Welcome to The Explainer. Today, we're going to demystify something you literally see happen every single evening. You know that moment at twilight when an entire street, or even a whole city grid of lights, just suddenly blinks on all at once? It honestly feels a bit like magic. But the tech behind it? Not magic at all. It's actually this incredibly practical, absolutely fascinating mix of physics and engineering.
Think about it for a second. The exact time the sun sets changes a little bit every single day, right? Because of that shifting schedule, cities can't just rely on someone sitting in a control room flipping a giant switch. And surprisingly enough, most of them don't even use a basic clock timer. Instead of just keeping time, these streetlights literally feel the environment around them to know exactly when it's time to light up the road.
Part 1. The brains. Sensing the light.
Okay, let's dive into this. The whole operation kicks off with the streetlight's sensory system. If you look really closely at the very top of a modern streetlight fixture, you'll usually spot this little plastic cap. That right there, those are the light's eyes. Tucked away inside is a tiny component called a light-dependent resistor, or LDR for short. And the secret to how this little guy works boils down to a fundamental physics trick called photoconductivity. Basically, when light energy hits certain materials, it actually frees up the electrons inside, making that material highly conductive to electricity.
So let's look at exactly how this plays out during the day. First, sunlight beams down and hits the squiggly track of the LDR. Second, that solar energy frees up the electrons in the material, which massively boosts its electrical conductivity. And finally, because a small electrical current can now easily flow through the sensor, it powers this tiny internal electromagnet, essentially an electronic switch. That energized switch then physically pulls the main power circuit open. It completely breaks the connection, so zero electricity can reach the actual street lamp.
And honestly, this brilliantly illustrates one of the most counterintuitive, mind-bending parts of this whole system. During the day, the light acting on the internal sensor is essentially on. The sun's energy is actively powering that tiny internal switch, which is exactly what keeps the massive streetlight off. It is quite literally the sun's energy that holds the street lamp off all day long.
But what happens when the sun sets? Well, it's a complete reversal. As the ambient light drops, that lack of light energy means those electrons get locked right back into place. The LDR's electrical resistance absolutely skyrockets, acting like a massive roadblock to that small sensing current. Because the current stops flowing to the internal switch, a mechanical spring just snaps the main circuit closed. Boom! The main power line is finally reconnected, and all that heavy-duty electricity rushes straight into the bulb.
Now, you might be looking at this highly sensitive light detecting setup and wondering, wait, why don't car headlights trick them? I mean, if a sensor detects light to turn off the street lamp, wouldn't a car's high beams or even a sudden flash of lightning accidentally plunge the whole street back into darkness?
Well, the engineers totally saw this coming, and their solution is beautifully simple: a built-in time delay. It's usually set somewhere between 30 to 60 seconds. You see, the photocell doesn't just react instantly to every random photon it sees. It actually requires a sustained, continuous change in darkness or daylight before it triggers any kind of reaction. So a quick flash from a passing car or a lightning strike, totally ignored by the system.
Part 2. The muscle. Powering the glow.
Okay, so once that mechanical spring snaps closed, thanks to the sensors we just talked about, we hand things over to the muscle of the fixture, the actual bulb. Now, how that lamp produces light depends entirely on how old the fixture is. Over the last few decades, city grids have transitioned through a couple of major bulb technologies. We've gone from high-pressure sodium to modern LEDs, and that shift involves major changes in the color of the glow, massive reductions in energy usage, and even changes in the warm-up time required to get the streets illuminated.
Let's start with the vintage standard, high-pressure sodium, or HPS lamps. If you remember that distinct, really warm, orange-yellow glow that used to define our highways at night, yeah, those were sodium vapor lamps. Instead of using a traditional wire filament, these bulbs contain a mix of gases and solid sodium metals, safely housed inside a vacuum tube. When that circuit closes at night, an intense arc of electricity jumps through the gas to heat it up. As the internal temperature climbs, the solid sodium actually vaporizes and starts to emit that fierce, iconic orange glow. And because of this literal metal vaporizing process, it takes a significant amount of energy and time. This is exactly why old streetlights take anywhere from 5 to 10 minutes to slowly warm up and reach full brightness when they first click on at twilight.
But cities are upgrading. The modern standard taking over our grids right now is the LED, or light-emitting diode. If the streetlights in your neighborhood emit a really crisp, bright white light, you're looking at LEDs.
There is no gas to heat up, no metal to vaporize. Instead, power moves through a tiny semiconductor chip. When electrons move through this semiconductor, they instantly release energy in the form of bright photons. This instantaneous process means absolutely zero warm-up time, and these incredibly durable chips can last for over 15 years without ever needing a replacement.
Beyond just the lifespan, the efficiency leap here is frankly staggering. LEDs use roughly 50% to 70% less energy than the older high-pressure sodium tech. To put that into perspective, for a municipality powering thousands or even millions of light fixtures every single night, this shift represents a massive reduction in strain on the energy grid. And ultimately, that saves millions in taxpayer dollars that can be reallocated to your community, all while vastly reducing the city's carbon footprint.
Part 3. The nervous system. The smart city future.
The evolution doesn't just stop with a better bulb, though. Modern streetlights are now forming a complete, interconnected nervous system. Today, a lot of cities are moving way past those simple standalone photocells. Instead, they're installing networked smart fixtures where each individual streetlight is fitted with its very own tiny computer node. These nodes communicate wirelessly, often using cellular or mesh networks, pinging data back and forth to a central hub monitored by city engineers.
And this nervous system gives engineering teams unprecedented control. Think about it. Instead of every light burning at 100% capacity all night long, a city can program the smart network to automatically dim the lights to, say, 30% capacity at 3 a.m. when the streets are completely empty. That saves an immense amount of power. Furthermore, if a bulb finally does burn out, a citizen doesn't even have to call it in anymore. The fixture instantly alerts the city's maintenance dashboard the exact second it fails.
So the crucial takeaway here is that a piece of infrastructure we entirely take for granted every day is actually a highly sophisticated, constantly evolving piece of technology. We started out exploring how a simple light-dependent resistor allows a lamp to feel the sunset, but as we look toward the smart city future, it leaves us with a pretty compelling thought to ponder. When every single streetlight is an interconnected computer, what else could your city's grid learn to feel next?